Welcome you all to this course on defects in material. Today we will discuss about the dislocations in FCC lattice. Okay. FCC lattice is the one in which most of the metallic materials crystallize. Okay. Many of the structural materials which are used like steels, nickel based superalloys, all of them have got the FCC crystal structure. So, to understand the deformation behavior, one should know what is the nature of the dislocation, okay, what is the Burgess vector corresponding to it, what are the types of Burgess vectors these dislocations can have, and what is the slip plane in which this dislocation will move. All this information is very much necessary. Okay. So, let us just look at the crystal structure of FCC structure. In the FCC structure, when we look at it, the vectors which we can have, that is the lattice translation vectors which it can have are the lattice parameter or A by 2110 or A111. That is, these are all the perfect lattice translation vectors. Okay. What we should know to define a perfect dislocation is that the perfect dislocation has got a Burgess vector which is a lattice translation vector. That means that when a perfect dislocation passes through the slip plane, okay, the atom above that plane or below that plane is shifted by a lattice translation vector. That means that it is moved from one lattice point to another lattice point. Okay. So, here what are the vectors which we can have? This is one vector which we can have. Here we can notice it that this is A by 2110 will be the lattice translation vector. This is another vector which we can have A100, and this is another vector which we can have which is A111. So, in FCC, increasing order of the magnitude of the translation vector if we consider, we can have B equals 110, 100, 111, and in fact I should write it as the set of directions. All these directions are equivalent in a cubic system, right. These are all the Burgess vectors which the dislocation can have. Okay. Then all are possible. Which is the one the system will try to have at it, as the Burgess vector for the dislocation? That is decided by which dislocation will have the lowest self energy. That means that if we take this to be the Burgess vector, we can try to calculate the self energy, because we know that the self energy equals, okay, half G into B squared. So, if we take this B squared value, then we will immediately notice that the one with this Burgess vector is the one which is going to have the lowest self energy. So, with the Burgess vector B equals half 110 is the one which will have the lowest Burgess vector. That also we can make out from here that this is the close packed direction in FCC. Okay. Other directions are not as close packed as this direction, right. So, now we have considered which is a vector. This, the multiplicity if we see, we can have 6 type of vectors can be there, correct, distinct ones, and both positive and negative direction if we can take 12 types of Burgess vectors which the dislocations can have, right. Now, the next question comes is that what is the direction, line direction which the dislocation will choose. Okay. The Burgess vectors we talked that though any perfect lattice translation vector could be a Burgess vector, potential Burgess vector for the dislocation, but the material will choose the one which has got the smallest self energy. That means that the one which has got the smallest translation vector. That in FCC, it turns out to be half 110. Okay. Now, what is the line direction which the dislocation will try to have? Okay. It can choose any direction it can take. Okay. Then the next question also which comes is that which is the plane in which the dislocation will move. Okay. That plane is decided in any crystal, okay, by the fact that as the dislocation moves, the resistance which the dislocation faces to its movement has to be minimum, or the lattice frictional stress is small. Okay. That also in any crystal structure, if we consider the just looking at the geometry of the crystal, we can tell that the one which has got the highest packing density, the plane which has got the highest packing density, in that plane the frictional stress will be less. Okay. On that basis, if we look at it, in FCC structure, 111 will be the slip plane, and this plane is called as the slip plane or the glide plane. Okay. This is the plane in which the dislocation can move. Okay.
So 111 plane is slip plane.
Is the slip plane.
And 110, half 110
is the Burgess vector of the dislocation. Okay.
For slip plane, we need highest packing.
No, slip plane, the density, atom packing density should be as high as possible in that plane, which because that other plane, this is something like the equivalent one which we can consider it is that you think of a road, okay, where the road, if it is being gravel and the gravel is put at distances which are very farther apart, or if the distances of gravel is put the same size of a gravel kept close together. If a vehicle has to move, the energy which it has to spend is more in the one where the gravel distance is large or the packing density is least. Okay. That is a perfect example. Okay. So then another type of a translation vector which is being used to define dislocations which are called as partial dislocations. This we will talk about it in future, not at present. Okay. But I just wanted to introduce the term that there is a partial translation vector also is used in the case of dislocation theory. Okay. Let us just for example, we talked about the different types of planes. Let us look at this 001 plane in cubic system. This is 1 bar 0 direction, this is 1 bar 1 0 direction, and this is the lattice translation vector A by 2 1 1 0. This is the lattice translation vector. In this hard sphere model, you can make out that these balls or the atoms are touching each other here, correct? So in this plane, there are two close packed directions are there. Okay, both of them could be the possible Burgess vector of the dislocation. Right? And if we take 110 plane, these are all the atoms on 110 plane. This is a close packed direction, and this is 010 direction which is not close packed, and this layer of atoms which is being shown actually the layer which is behind this. Okay. So only one close packed plane is there. So suppose in this plane the dislocation has to move, then it will be 110 plane, but the Burgess vector will be 1 bar 1 0. Okay. That is a possibility. Let us take the case of 111 plane. Here one can make out that the atoms are packed much better than even in 001 plane. Okay. And here three close packed directions are there. Okay. Half 1 bar 1 0, 1 bar 0 1 and 0 1 1 bar. Okay. all the 3 planes. So, in this particular plane we can have 3 types of dislocations with Burgess vectors corresponding to any one of these direction. Okay. And another thing also which you should notice it is that here the stacking sequence is a AB type of a stacking sequence, and in this 110 also AB type of a stacking sequence. Here it is an ABC type of a stacking sequence. Okay. This stacking sequence has something to do with the actually the structure of edge dislocation. For example, if you look at an edge dislocation, which we look at it, because so far when we have drawn the dislocation, all of them have been drawn for a simple cubic structure. So, in a simple cubic structure, okay, if we look at the Burgess vector, okay, is equal to essentially it is A100. It is essentially a movement of an atom from one direction to the another direction. Here what happens is that if you look at the stacking sequence in half 110 corresponding to this specific case, its a stacking sequence is an AB type of a stacking sequence, correct? When the stacking sequence is an AB type of a stacking sequence, if we add an extra plane or remove an extra plane, the translation symmetry has to be maintained. So, if we add any extra plane to it, we have to add, by adding a B plane, if we do it, then we will find that B will come. So, the structure is getting changed. So, that is not acceptable. So, if we add 2 layers, like here BA, 2 layers have been added, then one extra layer which has been added, okay. So, one can maintain, okay, the translational symmetry, okay, in the top as well as the bottom. To maintain the translational symmetry, minimum 2 layers have to be added. This one should keep it in mind for an edge dislocation in FCC. Okay. The same thing I had shown when an edge dislocation moves, okay, how the movement takes place. Okay. Here one can immediately make out these orange colored ones are the atoms are on the top, and the green blue colored ones are the atoms at the bottom. If you can remember one layer of an atom which has been removed, okay, from this, that is equivalent to say that one extra layer has been added here. This is where the defect is being present. Assume that extra layer is on top, bottom there is one layer is missing. If this dislocation moves from here to this point, then an atom from here has to move from here to this place. That is exactly what is being shown. When that atom moves from here to here, it is equivalent to this line has now shifted and come to this position. Okay. But another thing which is interesting to see also, that here when we look at it, 1 and 2 layers, actually 2 layers which are removed here, which one can make out that there are missing of 2 atomic layers are there. Though atom is only one which is being removed from every this direction, but if we consider as an atomic layer which is perpendicular to it, there is a 2 layer which is missing here. Okay. This way, by moving atoms from here to this direction, we can see that the dislocation line is moving towards right hand side, and finally this dislocation can come out of the sample surface. Now if we look at it with respect to the top layer, the bottom layer was actually at some particular position, correct? Now in this picture if we see it, the top layer remains at the same position, the bottom layer has been shifted towards the right by the Burgess vector. Okay. Now in this context I wanted to make one point which is very clear, is that one should understand the clear difference between the translation vector and the number of planes which are going to be in between. Okay. Because if we take this will be n111 vector from here to here in the case of an FCC lattice. Right? But if you consider the number of planes which are involved, this is from A layer, okay. Before we reach this layer, there is this one layer is there, then there is going to be another layer A, B, this is the C layer, then the A layer repeats itself. So between two vectors or between any vector, there can be many planes which can be there. Okay, that is what essentially is here. This vector is B, but between this, if we see, there are actually two planes are there. Okay. Okay. We have studied about another property of the dislocation, that when the dislocation forms in the material, the dislocation can not end within the material. That means that the dislocation should be interconnected. That is what essentially is being shown in this picture, that the dislocations are interconnected and the dislocation ends can come out of the sample surface at many points. And another important property which we have studied is that as the dislocations come and join, okay, at any junction if we see it, at that point if we take the sum of the Burgess vectors, okay, they have to be equal to 0, all the Burgess vectors which are there around that point. Okay. This has to be always kept in mind as far as the dislocations are concerned. So having this information, if we try to look at, okay, the type of slip systems which we can have in FCC lattice, we have 4 111 planes are there. Plus minus half 101 bar. So essentially on this one single plane, we can have a dislocation with a Burgess vector 1 bar 0 or a dislocation with a Burgess vector half 0 1 bar 0 or half 1 0 1 bar. This dislocation could be either an edge or a screw dislocation. Correct? If it is a screw dislocation, the line direction will be the same as the Burgess vector. If it is an edge dislocation, the line direction will be perpendicular to both 111, the plane normal as well as the Burgess vector. Okay. So three distinct dislocations are possible. Okay. Let us consider the case interaction of dislocations which are present in the same slip line. It should be similar for other slip lines also. We are considering one specific case, it is only this case. That is, similarly we can write expressions to find out what is going to be the Burgess vector of this. I would like you people to do it as an exercise and find out the number of slip systems which will be there in FCC. Okay. So suppose we assume that in the 111 plane there is a dislocation with Burgess vector half 1 bar 0. Okay. There is another dislocation with half 0 1 bar 1. Okay. And we assume that that's a sample. This is a plane in which one dislocation is there, another dislocation is there. Under the action of a stress which is being applied, these dislocations are moving. What sort of interaction which will take place? To find out that, we should find out if this reaction takes place, whether there will be a reduction in energy or not. Correct? That we can immediately find out whether there will be a reduction in energy or not by taking the b squared value. That will be here, it will be half, okay. Plus, let us take 0, 1. So what does this reaction will first lead to? The dislocation which is 1, 2 bar 1, correct? So the b squared will be here half, the value of b squared will be half here. Here what it will happen? It will be 1 by 4, 6, this will be equal to 3 by 2. That means that the energy, the self energy of the dislocation which has formed is higher than that of the dislocations which are trying to come together. Okay. That means that this reaction is not possible. So if a dislocation of this type is present, okay, with a Burgess vector, they will repel each other. Okay. Let us consider the case where the Burgess vector of one dislocation is half 1, 1 bar 0, and the other one is half 0, 1, 1 bar. Okay. If this is the Burgess vector of the dislocation, then these two reactions, this reaction if we consider, if these dislocations are moving, whether they will attract or not, will be decided. We can look at the dislocation reaction. This will give rise to half 1, 0, 1 bar. That means that here the Burgess, if we take the b squared value to find out the self energy of the dislocation, or the Frank criterion, that is what we are trying to find out. This is half plus half, and this side is going to be half, correct? So that means that when these two dislocations join together and form another dislocation, this dislocation also will be lying in the same slip plane. Okay. These two join together and vanish, and new dislocation has formed, but that dislocation has got a Burgess vector half 1, 0, 1 bar. That means that there is a reduction in energy. This reaction will take place, correct? So this is a natural attraction. This reaction is possible. Here the dislocations will always, the stress field will be such that they will be repelling each other. But under the action of a force, these dislocations can be made to move and cut across each other. Okay. So, but definitely when these two dislocations are there, when they move, one dislocation is like this and another is like this, when they try to move, they will cut across, but they will never join together to form another dislocation. That will not happen. This part of it will come a little bit later. Okay. You understood this part of it? Okay. Here what we have considered is dislocations which are being present, okay, in the same slip plane. So if you consider an FCC, when the dislocations are moving in the same slip plane, for a perfect dislocation, this is the only type of a reaction which can happen. Either the two dislocations can attract each other and form another perfect dislocation, or the two dislocations can repel each other, correct? What is the other type of a reaction which can take place when a material is being deformed? Dislocations are moving in one plane, and in another plane also the dislocations are moving. Then these dislocations can try to interact. So it could be any plane in which the dislocation which is lying or which is moving in that plane can interact with dislocation which is moving in another plane. Okay. Let us take that case. If these two cases we have considered, then we have considered the various types of interaction between dislocations lying in different slip planes for perfect dislocations. All cases might have been considered. So suppose we take this is one plane, okay. The other plane is 1 bar 1. This plane will be inclined with respect to this particular plane. in this particular case, what are the Bijus vectors which it can have? 1, half 1, 1 bar 0. This is 1, correct? Plus minus. And here plus minus half. One. The third case is these are all the type of Bijus vectors the dislocation lying in this slip plane will have. Okay. Let us assume the case that a dislocation is there in this plane which has got a Bijus vector half 1, 1 bar 0. Another dislocation is there in this plane which is moving in this plane which has also got a Bijus vector half 1, 1 bar 0. That is essentially what we are trying to do is this is one slip plane. Okay. That is a dislocation which is moving in this plane. That is a dislocation which is moving in this plane, and a dislocation in this plane is also moving in this direction. We assume that. If they are moving like this and the Bijus vector of the dislocation is half 1, 1 bar 0, okay, in both the planes, and you assume that this is 1, 1, 1 plane, this is 1, 1, 1 bar plane. Okay. Now what will happen is that if they are moving, okay, and another has got a Bijus vector, so this will be plus half. These are dislocations with the same type of a Bijus vector. This will give rise to half 2, 2 bar 0, that is essentially 1, 1 bar 0. That means that this reaction, if you see, it is half, half, this will be 1. So, in general this sort of reaction does not occur. Suppose the dislocation which is going to be there on this plane has got a Bijus vector half 1 bar 1 0. Okay. And the line direction is also either the same or the line direction could be different. Okay. You assume the case where the line direction is the same as the Bijus vector. That means these are both screw dislocations, and these screw dislocations, if you look at it, these two when they intersect, okay, the common direction which is common between these two planes is 1, 1 bar 0 direction. So when they reach there, they will just annihilate, right? This reaction, if you consider half 1, 1 bar 0 plus half 1 bar 1 0, this will give rise to Bijus vector will be 0, right? So that means that these dislocations attract each other and annihilate. Suppose these dislocations are H dislocations which are moving, okay. As they come here and then they join, okay, meet here at this point, since the common direction is 1, 1 bar 0, these dislocations will have to, okay, change the character from when they come and meet and join together, the character has to change and it has to become a screw character. Okay. Then only we can have them join together at this point, correct? So this is the second case which we considered. Okay. So if they have the same Bijus vector, they repel. Okay. If they have a Bijus vectors which are different, okay, then they attract. Let us look at the case where the Bijus vector of the dislocations are different. Because here why we have considered is that between this plane and this plane, okay, one Bijus vector, dislocation of the Bijus vector is common to both of them. Now let us consider the case where this has a bias vector, that is in the plane 1 1 1 bar, the dislocation has a bias vector half 1 0 1, and the dislocation which is on the plane 1 1 1 has a bias vector which is half 0 1 1 bar. Okay. Let us look at this reaction 1 0 1 plus half 0 1 1 bar. This will give rise to dislocation correct. This is what the dislocation is. That means that in this reaction there is a reduction in energy. That means, like in this case, one dislocation is moving in this and another dislocation is moving in this slip plane. Okay, suppose this is 1 on 1 bar and this corresponds to 1 on 1. Okay, this dislocation is the line direction, this dislocation is moving in this direction, this dislocation is moving in this direction. There is a chance that they will attract each other, and at this particular point they can join together and they can have the bias vector half 1 1 0, because this is an attractive interaction. So this type of a reaction is allowed because the energy gets lowered when these two dislocations come together and join. They always try to minimize the energy. In this case, now let us look at what will be the line direction which this dislocation will have. Okay, the line direction when they come and join together, that should correspond to this line direction where they meet. So for a plane 1 on bar and 1 on 1, the direction which will be common to both of them, what will be the direction? 1 on bar 0, correct? So that means that when these dislocations interact and form a dislocation at this junction, the line direction of the dislocation is 1 on bar 0. Okay. This is the bias vector. Okay. So that means that the new dislocation which forms has u equals 1 on bar 0, b equals half 1 on 0, and then taking u cross b, we will be able to find out the plane normal. So what will be the slip plane? The slip plane will be turning out to be the n here, it will be turning out to be 0 0 1. That means that for this dislocation, its slip plane, since the line direction is perpendicular to this one, this is an H dislocation, and the slip plane turns out to be 0 0 1 plane. That means that that plane is not a close packed plane in FCC. So this dislocation will find very hard to move. So this sort of reaction leads to dislocations which are called as Assail dislocation. Assail means that this dislocation is not able to move, and these reactions, this is also called as a Lamar lock. Okay, that is when a dislocation is, when different types of dislocations are moving, okay, an interaction of this type will generate a Lamar lock. Okay, and this dislocation, since it is not able to move, for other dislocations which are coming in other slip planes, now it has to overcome these dislocations, because this is what it contributes to. When we deform a material, we call it as a forest dislocations. Of many dislocations which are generated, By this sort of a dislocation reaction, we find that many of the Assail dislocations which can easily move in the slip plane, some of them have transformed into a Assail dislocation which just will not move. So those dislocations act as obstacle to movement of Assail dislocations. This is one way. This is the only way in which for a perfect dislocation a Assail dislocation could be generated. Okay. We can consider here another case in this reaction. On this plane 111 bar, we have a half 101. On this plane 111 plane, we assume that we have a dislocation with a bias vector 1 bar 1. In this reaction, if we consider it, it will be half 101 this will lead to correct. This will be the bias vector of the reaction when they interact. That means that the self energy of the dislocation increases. So these dislocations will repel each other. When these dislocations repel each other, okay, under thermal conditions, they will not come and join together because they don't attract. Or even if you apply a force, lot of force has to be applied, because when we deform a material, we are giving an external energy to it. So the reactions which are not favorable under thermal equilibrium conditions, we can make those reactions occur in the material. Okay. But when these sort of dislocation are there, since what is the only type of an interaction which we can have in these sort of cases? Suppose one dislocation is present, another dislocation is coming from this region, okay, in the same slip plane. Only way they can interact is that this dislocation can pass through and come to this side by cutting this dislocation. Okay. One dislocation is there, another dislocation comes through it, cuts through the dislocation. When it cuts through this dislocation, there will be some small step will be generated in most of these cases. Okay. These steps are called either kinks or jogs, that we will be talking about it later. But for the present, we should understand that this sort of reaction, the dislocations will never interact, but when we are applying a force, they try to cut through that, and when it comes out, this dislocation will be there with maybe with a step like this. This dislocation might have come out with a small step which has been generated in this sort of. By this process, also we can make out that the length of the dislocation has also increased. Correct? This is one way in which the length of the dislocation increases in the material. Okay. So far what we have considered is different types of reactions. Okay. That is, first, dislocations in a slip plane. Okay. And these are all perfect dislocations. What is the interaction between these dislocations we have considered? Okay. Attractive as well as repulsive interaction. The same thing like what we have talked about it. This can happen whether the dislocations are moving in the same slip plane or in dislocations are moving two different slip planes, the same thing can happen. So essentially these are all the only types of reaction which can happen. That is, if the dislocations are moving in the same slip plane, then they can produce, okay, a third dislocation which is also Assail by interaction of them. But if the dislocations are moving in two different slip planes, if it is attractive, okay, in one case a Lamar lock could be generated. In another case, if they have the same bias vector in both the slip planes, not bias, opposite bias vectors, then they will annihilate. If they have the same bias vectors, they will try to repel each other. Okay. So, these are all the type of reactions which can happen for a perfect dislocation in any material. An ideal example which we can consider is aluminum. Aluminum is one sample, okay, where the stacking fault energy is very high. So, all dislocations are perfect dislocations. So, these are all the type of reactions by which, okay, dislocations can interact. Also, dislocations can generate forest dislocations in the material.